50、49、48、47、8、7、6、5、4、
メインエンジンスタート。
メインエンジンイグニッション。
1、0、
SRBA 点火、リフトオフ。
SRBA イグニッションand lift off。
希望に満ちた明日へ。国際宇宙ステーション補給機コウノトリ2号機を搭載した H2B ロケット2号機は平成23年1月22日午後2時37分57秒に種子島宇宙センターから打ち上げられました。
Welcome to the Kakuda Space Center. Kakuda Space Center is a division of the Japan Aerospace Exploration Agency, which has been leading Japan's aerospace research and development for a decade. Here, we provide you a short tour of our facilities and activities. Our daily life is getting more convenient. For instance, forecasters predict the weather with accuracy by using satellite photographs. All kinds of entertainment, movies, and foreign news are now at your choice, thanks to satellite broadcasting. This is a navigation system that supports cars, airplanes, and ships to travel to their destinations. And with a similar function installed in a cell phone, you could reach anywhere you want with no difficulties. Have you noticed that all these modern conveniences have one thing in common? It's a rocket. Yes, rockets transport the satellites that make all these technologies possible. The rocket engine, let's call it the heart of the rocket, propels gas to produce the thrust that lifts the rocket into outer space. Amazing, isn't it? Here at Kakuda Space Center, we are leading the research and development of Japan's rocket engine, which are now among the world's finest. Currently, the H2A is Japan's flagship rocket. It is a two-stage rocket with liquid propellant engines. A liquid propellant rocket engine is the one which uses liquid hydrogen as fuel and liquid oxygen as an oxidizer. It is the world standard propulsion system for current rockets. And of course, the first stage LE-7A engine and the second stage LE-5B engine both belong to this type of engine. H2A lifts off by the power of the booster engine, LE-7A. When LE-7A uses up all the liquid hydrogen fuel, the first stage is separated and the second stage, LE-5B, kicks in to push the rocket to the target satellite orbit. These engines are also adopted for the latest H2B rocket. With H2B supplying materials to the International Space Station, we are doing our part as a member of the world space community. Using the test facilities at Kakuda Space Center, the entire LE-5B second stage engine and the components of the LE-7A, the first stage engine, have been tested and examined for development and verification. Now, let's see the mechanism of a rocket engine taking the LE-7A engine as an example. LE-7A adopts a staged combustion cycle and its thrust force is about 1,100 kilonewtons. Inside the engine, the hydrogen turbo pump rotates about 42,000 RPMs and pressurizes the liquid hydrogen fuel. And so does the liquid oxygen turbo pump for the oxidizer, with a rotational speed of about 18,000 RPMs. In the turbo pumps, the propellant's pressure is raised to 30 megapascals. The propellants go to the combustion chamber, where they are burnt at the pressures of 12 megapascals. Then it's ejected through the nozzle. The LE-5B, the second stage engine, adopts an expanded bleed cycle that is quite robust. Acceptance test of the LE-5B is conducted in a simulated high-altitude test stand at Kakuda Space Center. Firing tests are carried out to check that performance is in the acceptable range for the flight. After a while, from the launch, LE-5B starts in the near vacuum region at an altitude of more than 30 kilometers. So the thrust of LE-5B should be measured by conducting the firing test in a low-pressure condition, simulating the real flight environment. The white smoke you see here is a tremendous amount of vapor that is used for the ejector system of the facility. The ejector system lowers the pressure in the test chamber. Firing tests are monitored in the control and measurement room. In the test chamber, the actual LE-5B engine is fired in a closed low-pressure condition. After examining the functions and thrust performance, the engines are delivered to Tanegashima and mounted on the rocket. A variety of development tests are also conducted, and the data will be used for future improvement. Now, here in this part, we introduce the research and development of rocket engine components. First, the turbopump. The liquid hydrogen turbopumps are tested in the propellant feed system test stand. Also, the liquid oxygen turbopumps are tested at the high-pressure oxygen turbopump test facility. Both facilities can simulate actual flight conditions, which help the development of turbopumps with a high level of reliability. Cryogenic inducer test facility is used to study the cavitation phenomenon in the inducer of the turbopump. The world's finest image of cavitation bubbles around the inducer and liquefied gas was caught in this facility. The results will contribute to understand the phenomenon along the numerical analysis. The bearing is a component that holds the pump shaft, which rotates at ultra-high speeds. The seals prevent the mixing of high-temperature gas driving the turbine and very low-temperature fuel. Both are studied at Engine Mechanics and Tribology Test Facility. The test results are compared with the results of numerical simulations. And here comes the study of combustors and nozzles. Studies on nozzles using different types of fuel, such as hydrocarbon like methane and alcohol, are conducted at a high-altitude test stand for rocket engine. Also, dual bell nozzle and aerospike nozzle, which potentially have a high performance, are being explored here. The visualization tests of the fuel injection using liquid hydrogen or methane and studies of the improved combustor are being conducted at the Liquid Rocket Combustion Test Facility. In the future, space development will become even more active and more efficient space transportation systems will be needed. In Japan, the studies of an original shuttle or space plane is underway. With the ability to take off from a runway like present-day jets, it will be able to shuttle passengers and cargo into orbit. For future activities on lunar surface, more people and cargo will have to be transported to the orbital platforms. The spaceplane will be vital for that purpose. The spaceplane's main advantage is that, unlike current rockets, it is fully reusable. Along with cheaper launch costs, the flight will be safer and more comfortable. However, the new spaceplane will require a new high-performance engine. Our answer is a combined cycled engine, which embraces both rocket and ramjet engine technologies. Ramjet is a very high-speed jet engine. Its ultra-high-speed version is called scramjet. The combined cycle engine keeps high efficiency through all the flight speed by switching the operation mode. At takeoffs, this engine uses rocket mode, and then at Mach 3, or 3 times the speed of sound, the ramjet mode kicks in. Gaining speed in ramjet mode and later in scramjet mode, the spaceplane accelerates into space where the rocket mode takes over again. Why the ramjet mode? Actually, the heaviest load on a rocket now is the liquid oxygen, comprising 70% of the rocket system's total weight. Instead, the ramjet uses oxygen for the atmosphere in flight, but drastically reducing the amount of liquid oxygen, the vehicle's payload can be increased. In order to realize the combined cycle engine, it is necessary to verify the performance when flying at a super high speed. That's why we are making various combustion experiments on the engine using special facilities, and also we are carrying out numerical simulations. When the spaceplane re-enters Earth's atmosphere, flow around the vehicle is superheated and the temperature increases to more than 10,000 degrees Celsius. To study the effect of high temperature air on the vehicle, the flow is simulated in our high enthalpy shock tunnel. It is the world's largest and best facility of its kind, and the only ground facility capable of reproducing such extreme flow. The animation shows a function of the tunnel. First, the piston fires, compressing the helium which breaches the diaphragm. Then the second tube, a strong shock wave is formed, and it creates a high pressure and a high temperature gas. The gas is then released to the experimental model in the test chamber. With this shock tunnel, extreme conditions such as airflow around the spaceplane during the re-entry phase and the flow inside the combined cycle engines that fly at speeds in excess of Mach 8 are simulated and studied. Well, we hope you now have a better understanding of the activities at Kakuda Space Center. For more detailed information, please take advantage of our exhibition rooms. That's all for now. We sincerely hope you have a deeper interest in space and the Earth through our presentation. Thank you for coming, and we'll see you around the galaxy. Happy landing!